What's up, guys? Another video on energetics, looking or continuing to look at Hess's law in particular, and we've got enthalpy of combustion data to work with. Before we start though, please like, subscribe, share with anyone you think might be interested. I want this to reach as many people as possible so it can help all those people. Let's get into it. So enthalpy change, let's start off with our definition. Enthalpy change of combustion, we've got our little scaffold here, our little template for all our definitions. When 1 mole of a substance, let's make that smaller, is completely burnt in excess oxygen in their standard states under standard conditions. Okay, so essentially why we're often going to have these sorts of questions is enthalpy changes for particular reactions can be quite difficult, but it's very easy to take the reactants and the products of those and just burn them, heat up some water and calculate our enthalpy change with calorimetry like we've looked at before. So let's do a couple of examples. First of all, calculate the enthalpy of formation of ethanol given the following. So again, worth reflecting on our definition of enthalpy of formation. Again, think enthalpy change substance is formed from its elements in their standard states under standard conditions. So here we've got our elements, which is C2H5, our compound, sorry, C2H5OH. We need to think about the constituent elements that form it. So there we've got 2 lots of carbon solid plus not 5 but 6 hydrogen, so 3H2 gas plus half O2 gas. And the reason why we're dealing in halves here and we wouldn't normally in reactions is so we can fit that rule of having 1 mole of our substance, and our substance here is ethanol. So again, this might be quite difficult for us to work out what the value of is, so we can just take hydrogen, carbon, ethanol and burn them, see what the change is. And what do we make when we burn them? So we make 3 lots of H2O plus 2 lots of CO2. And again, we can think about our arrows here. Again, remember our definition. So when 1 mole of a substance is completely burnt in oxygen, so we're going this way, okay? Water and carbon dioxide are our products. These are our products of combustion, and these are the things that we're combusting. So these are our arrows. Next, we can start inputting our values. So we've got 3 lots of hydrogen, so 3 lots of minus 286. We have 2 lots of carbon, so 2 lots of minus 393. Obviously we're trying to work out this, and then we've got our value for ethanol minus 1371. Now we think about which direction our arrows go, and we're trying to work out this, so we go the opposite way. We can't go this way, so we go around here. Now we can start plugging our values in. For starters, we're going with the arrow. Happy days, we don't need to change the sign. Let's keep it in brackets though. So we've got 3 lots of minus 286 plus 2 lots of minus 393. Now here we're going against the arrow. So this time our sign will change. I like to just do a minus here and keep everything the same. Minus 1371. Now we can plug all of that in our calculator and we get to minus 273 kilojoules per mole. Sorts of mistakes that can happen here are not multiplying by 3 or not multiplying by 2 in this case, and also forgetting to change the sign because we're going against the arrow. These are our common mistakes. Also, sometimes people fiddle around and get these arrows the wrong way around as well. So just those are the things to be quite mindful of. Let's do another one. So here we're calculating the enthalpy of combustion of propane given the following data. So this time we've got the enthalpy of combustion data for carbon and hydrogen again, but we only have the enthalpy of formation for C3H8, which is our propane. Okay, so we're going to work things out slightly differently. We can write this enthalpy of formation first of all though. So we've got our C3H8s and our constituent elements. We've got 3 lots of carbon plus 4 lots of H2 gas. And again, think about what we create when we burn them. When we're drawing these, we can sort of ignore oxygen, not really balance out those oxygens. Just think about what we're making here. So we've got 4 lots of H2O plus 3 lots of CO2. Because there's an excess of oxygen, it doesn't matter too much. Okay, let's plug in our values. So for starters, we have our enthalpy of formation values. We've got our minus 103. This is the value we're trying to work out, our enthalpy of combustion for propane. And then we've also got these values. We've got 4 lots of minus 286, and we have 3 lots of minus 393. Now we can start to work this out. So this is what we're trying to work out. We can't go this way, so we go all the way around. Now I can start working this out. So for starters, here I'm going against the arrow. I do minus 103. Again, this minus is a result of going against the arrow. This time I'm going with the arrow. So I do plus, and brackets, 4 lots of minus 286 plus 3 lots of minus 393. Plug that all into the calculator. Sorry, 2,220 kilojoules per mole. Perfect. So this is the similar question. I'd like you to give a go and check your understanding. I'll go through the answers to that at the end of the next video. For now, let's go to last video's question, which was a slightly longer one. So B part 1, at a high temperature, carbon undergoes combustion when it reacts with oxygen, suggests why it is not possible to measure the enthalpy change directly for the following combustion reaction. So remember, when we're talking about enthalpy of combustion, we're talking about 1 mole of a substance being completely burnt in oxygen. Carbon monoxide is not that. Say that carbon dioxide will be produced. That's our whole explanation, right? 2, state Hess's law. Definition. I mean, it's important to remember definitions to help your understanding, but you also get some bonus marks as we go through. So enthalpy change is independence of the route taken. State the meaning of the term enthalpy of combustion. Again, we've got our little scaffolding that we've just done. So it's when 1 mole enthalpy change when 1 mole of a substance is completely burnt in oxygen under standard states, under standard conditions. Next, use the standard enthalpies of formation in the table below and the equation to calculate the value for the standard enthalpy change for the extraction of iron using carbon monoxide. So, on the bottom, I'm very much just going to do our things here. One thing to point out though, remember enthalpy of formation is talking about standard states and standard conditions, which is why we do have a value for Fe liquids, because iron is generally as a solid. So we've got 2 lots of Fe solids. We have not 3 but 6 lots of oxygen. So it would be 3 lots of O2, sorry, plus 3 lots of carbon solid. And again, these are enthalpy of formation values, so we think about which way the arrow goes. They're going up. Now I can start inputting my values. So I've got minus 822 here, 3 lots of minus 111 here. This is the value we're trying to work out. And then I've got 2 lots plus 14, as well as 3 lots of minus 394. Now again, because I'm trying to work out this and I can't go this way, I go an independent route here. For starters, I'm going against the arrow here. So there, I'm going to do my minus on the outside, and now put everything else in brackets. 822 plus 3 lots of minus 111. Next, I'm going, next I'm going with the arrow. So I'm going to add here. So plus, again, all in brackets, 2 lots of plus 14 plus 3 lots of minus 394. Plug that all in, and we get to a very strange number of plus 1 kilojoule per mole. Again, do it a couple of times in your calculator just to make sure. Last couple of bits. Part 1, write an equation for the reaction that represents the standard enthalpy change of formation for carbon dioxide. Remember, elements, standard state, standard conditions. So we've got CO2, gas, and that's formed from carbon solid plus O2 gas. The state symbols are going to be important there because our definition says that we need our standard states and standard conditions. So if you forget to do the state symbols here, marks have been lost. And last one, state why the value quoted in part C for the standard enthalpy of formation of CO2 is the same as the value for the standard enthalpy of combustion of carbon. Again, what would combustion look like? It would look exactly the same. Carbon burnt in excess oxygen, so it's the same reaction. Hope that's helpful. See you next time. Happy revising, guys. Again, like and subscribe.